So this is our last talk, and I know that you are tired. So it won't be mind-blowing, but you will require your laptops because I have some exercises to do. So here is a repository I want you to clone, and I also sent a message to the random channel in Slack. So please check this channel. Here's a link there, and I want you, while I'm starting, to download the repository, build the product, and run the empty test. It does nothing, but you will just be sure that everything works if this test passes. All right? So please do that now. Good. So we'll talk about concurrent algorithms, and if you ask, what should we do to create a new one, to design a new algorithm? Then I would say that you need to learn a lot of material. You need to learn a lot of books, study them properly, implement a lot of things. And then you need to attend such events as SPTDC. You need to attend top-tier conferences. You need to learn from the experts. You need to learn the state of the art. And then when you have a lot of expertise, a lot of experience in implementing something that already exists, then it's easy to design new algorithms. But you know what? There are a lot of textbooks, right? A lot of papers. All of them are available online, and anyone can read them. And for you, it will take hours, days, months to learn all of this. But we have another guy that can grab all this material quickly, right? And maybe if we teach ChatGPT or any other large language model, it can assist us with building concurrent algorithms. So let's try to build something simple, but still not so straightforward. Let's try to build a bounded queue. So it's a queue, but of a fixed capacity. So when you add elements successfully until the capacity exceeds, and then additions fail. So this add returns false. And poll works like any deque operation for any queue. If the queue contains elements, it returns the first element. If the queue is empty, it returns null. Okay, let's ask ChatGPT to build such a concurrent queue, and we want it to be non-blocking, right? But otherwise, you can simply use a global log, synchronize all the operations using this log. It will work, but the performance will be not that we want. So, okay, let's try to make it non-blocking. And let's try to use the existing implementation of a queue, a concurrent linked queue from the standard library. So I asked ChatGPT for you, and here's the suggestion. So the idea is that we have an already linearizable correct queue under the hood and an atomic counter that maintains the number of elements in the queue. So we can understand whether the queue is already full or not, and fail in the enqueue procedure if the queue is full. That's how it works. This is the exact code from ChatGPT, including the comments, actually. So to add a new element, we first check whether the number of elements is already equal to the capacity of the queue, and if so, we say, no, we can't add a new element, and we return false, right? Otherwise, the queue is not empty. We add a new element, this element, to the underlying queue, and then we increment the size and finish successfully. And the poll operation, it checks whether the queue is empty or not. If the queue is not empty, it extracts the first element and decreases the size. So do you think that this implementation is correct? Anyone thinks that it's incorrect? Oh, good, nice. But how to understand that? How to understand whether this implementation is correct or not? Actually, it's not trivial, because here maybe the implementation is simple, but the algorithm is more complex, so then it's not easy to do that, to analyze the code. And of course, we need to write tests. But the problem with the classic tests is that they usually cover only easy to verify scenarios like adding elements from one thread, retrieving from another, and checking that we retrieved the exact number of elements that we added to the queue. And all these tests are pretty similar. So you run these threads, you run the operations, you try to verify the results somehow, and there is a lot of boilerplate code. But what is most importantly is that, okay, you have such a test, you can have such a stress test, and then it fails. What's next? What will you do with this error? Because you randomly execute a lot of operations, and at some point it just fails, but you don't know why. It just fails, and you need to find the error. And how to do this? Usually you just read your code over and over and over and over until you realize that in this particular line of your code it's buggy. But what you really want is to have some framework that can simplify constructing these tests, and that can simplify debugging of such errors. So let's try to write an ideal test. Okay. So how would you write an ideal test? So of course you create some class if you deal with Java or Kotlin, and then you want to specify your data structure. Like here, we just say, okay, we want to test that our bounded queue implemented by ChatGPT is correct, and the queue capacity is 1. We just need to choose something, right? Then we list all the operations. In our case, it's add and poll. We simply list them. We don't do anything else. And then we want to run some magic button that checks whether this solution is correct or not. So, do you want such a tool? No, nobody. Then we should finish. But actually, that's pretty much what you want. You want to tests to be declarative. You want to list the data structures, run the magic button, and see whether your data structure is correct or not. You want some magic, definitely, yeah. And here's the tool we've been developing at JetBrains for a long while. It's called Lincheck, kind of linearizability checker, but it can test not only for linearizability. And that's exactly what it does. So with the Lincheck, the only difference is that instead of this magic button, here is a specific button. Like here we say that, okay, we want to use model checking, and we check this data structure. All right. So what I wanted to do is to clone the repo and run this bounded queue GPT Lincheck test. So let's spend 5 minutes on this, and then we continue. So here's our Lincheck test, and let's run it. So we run it. We wait for several seconds. And now, yeah, we see that this test has failed. So here's the scenario. We have two add operations, right? And both of them succeeded. But in the test, we have a queue of capacity 1. So it's something strange. But let's go back to the presentation. So here's this result. For your convenience, I will present results this way, not in the IDE. And we need to analyze what is wrong and why it is wrong. But the first question is, what do we want from this data structure? What is correctness? So what is correctness of a concurrent data structure? How to define it? So in the first day, I think you learned that. It's linearizability. So if you, by default, if you say that your data structure is correct, you mean linearizability. Of course, there are various relaxed contracts. Sure, but usually if you see that your data structure is thread safe, atomic, or just correct, usually it implies linearizability. And to remind you, we call an execution linearizable if we can express it with some sequential execution that does not violate the happens before order. So it doesn't violate the program order and the synchronization between threads. And also, it produces the same results. Of course, it's simplified version of the definition, but the intuition is that. And for example, here's a bounded queue of capacity 2. And we have two threads. In the first thread, we add A and poll A. In the second thread, we add B and poll B. Is it linearizable? Yeah, obviously it's linearizable because we can find a sequential execution that explains these results, like this, right? Okay, another example. Here we add A and B in the first and second thread, but we poll B in the first one and extract A in the second thread. Is this one linearizable? Can we find a sequential execution that produces the same results? Yes, we can find one. So we can say that, okay, the execution started with the first thread. So we added A first, then we add B, extract A, switch back to the first thread, and extract B. Okay, another example. So here we have add A and poll B in the first thread, and we add B and C in the second one, and extract C at the end. Is it correct? Is this execution linearizable? So who thinks it's correct? Who disagree? Okay, let's think for a while. Let's try to find an execution that explains these results. Okay, actually, we can't find such an execution. Because for poll in the first thread to extract B, add B should happen first, right? So the execution must start with add B. Then we add A and poll B. And it's important that this order is the only order that is possible to explain this scenario, because we have bounded queue of capacity 2. And you see this add C should succeed. So this poll should happen before adding C to the queue. So for add C and poll B to succeed, the prefix should be this. But then, if we call poll, it can't return C, it returns A. Because we have a queue here, not a stack.
But we can add E's and add C's and add A's and poll B's.
So the question is that, okay, why not to explain it differently? Like, we add B, then we add C, then we add A. But if we do that, then the queue capacity exceeds. We have bounded queue of capacity 2. And we can't add 3 elements to successfully to queue of capacity 2. So we can't find a sequential history that explains these results. So we are sure that it's incorrect, right? The implementation is incorrect. Okay, but in our case, it's even much simpler. We just have add 1 and add 2. And we have a bounded queue of capacity 1. Both of these additions succeeded. And obviously it's not linearizable. We can't explain this in the sequential execution because one of these adds should fail, right? And what is important is not that Lincheck just gives you this small scenario. No, it also explains how to reproduce the error. It gives you a detailed trace to analyze your error. So let's try to understand what just happened. So we have this trace. We have our add function because that's the only function we need in this execution. And on the left, here is a queue state. So here's the underlying queue and the size counter. So the execution starts with the checking whether the queue capacity has already exceeded. No, it's not. The size is 0, capacity is 1, so we proceed further. Then we add 2 to the underlying queue, and the execution switches to the first thread. So now we switch to the first thread and invoke the add operation. So since the size counter was still 0, it hasn't been updated yet by the first add in the second thread. So the add on the left successfully added 1 into the queue, changing the size counter to 1. So now the size is 1 and the queue contains 2 elements. And then we switch back to the second thread and increment the counter. Now the size of the queue is 2. That's higher than the queue capacity, but that's what we did. That's what ChatGPT suggested. And we clearly see why it's incorrect, because this size increment and the addition to the queue, they happen non-atomically. And if you do something in between, you can exceed the queue capacity. That's what Lincheck gives you. It gives you not only the knowledge that you have a bug in your data structure. It gives you a concrete trace that leads to this error. Now I will explain how Lincheck works, how this magic works, because obviously there is no magic behind it. So, in some sense, Lincheck is a mix of a fuzzer and a model checker. So first of all, when you declare all these operations, Lincheck generates a lot of different concurrent scenarios, putting these operations randomly into concurrent threads, generating arguments randomly. And that's the the fuzzing phase. And then each of these scenarios is examined via either stress testing, that's how you usually write tests, right? Or how, for example, the GMH tool for Java works. Or we have a better option, we have a model checker in Lincheck. And model checker controls the execution, so it when you find an error with the model checker, then you do know how to reproduce it, because that was Lincheck that decided how to execute this scenario. And finally, so after we ran the execution and got results, we need to verify whether these results are correct or not. So how do we do that? Remember, we said that the execution is linearizable if we can express it with some sequential history. And that's what Lincheck does. It tries to find the sequential history that explains the results. And to do that, it uses your data structure sequentially. It runs it sequentially to generate such histories. And if there is no such history that explains the results, then you have a bug. And Lincheck test fails and gives you an interleaving that leads to the error. So here are just the 3 simple steps. So first, it generates ton of random scenarios, examines them in either stress testing or model checking mode, and automatically verifies whether the results are correct. Because we don't need to know the data structure semantics. Because for linearizability, we don't care. We assume that, okay, it's already correct in the sequential world. So we just need to find some history. Okay. And a couple of words about the model checker. Because to control the execution, we use bytecode transformation. And here is a simple example. So, because for the bounded queue, it would be too much, there is a lot of code, but here is just counter. We have a counter and we try to implement the increment and get function. So we read the value, increment it locally, then write it back, and read it again at that. Okay? And the bytecode is the following. So we read the value via get field instruction, then we write the value via put field, and read it again via get field. And what Lincheck does, that it looks up for all the shared memory accesses through this get field and put field. Through some weird ways like unsafe or handles, atomic field updater. So there are plenty of ways to mutate shared memory on JVM, and the check just supports all of these ways. And then it adds special functions before the shared memory accesses. So here, it's like, okay, before reading the counter, before reading something, we call before it. Before write something, we call before write. And the check, when this function is invoked, decides whether to continue the execution or switch to another thread. So if we write a test for this obvious incorrect counter, this test fails, and what was happening under the hood, that there were these before read, before write calls, and after each of them, the check decided whether to continue or whether to switch. And in this particular case, before reading the counter first time, the second thread, it decided to continue. Then, before performing a write, it decided to switch to the first thread. So we switch to the first thread, then we continue. we switch back because the execution has ended in the first thread, and we finish the execution in the second one. And on each of these shared memory accesses, Lincheck decided whether to switch or continue. And in Lincheck, we studied different such interleavings. So now it's a pretty simple model check, and we're working on a better one with the partial order reduction in order not to study similar interleavings, but to study only one of them, and all other interleavings from the same class, we just don't care about them. They're the same. But right now it's a simple model check, and surprisingly it works pretty well. We can test very huge data structures using it. Okay, so here's a good point for questions, and then we'll try to do something with Lincheck. Questions? Any questions? No questions. Okay. So I have some exercises. For that, we need to work with the microscope queue. So who knows the microscope queue algorithm? Almost everybody. So let's quickly go through it. So in the microscope queue algorithm, it's a queue which is built on a linked list, and so you have head and tail pointers, you have next pointers to construct this linked list. And here is a trick that the first element is stored not in the node where the head pointer references, but in the next one. Why do we do this? Because we need some way to specify an empty queue. And for simplicity, we say that the queue is empty if there is only one node in the list. Okay, it's a dummy node. It doesn't contain an element. I mean, logically, physically it can, but logically there is no element. And this queue is empty. So, and here, in this example, we have 4 nodes. The first node is the dummy one. In the next 3 nodes, we store elements. All right. So here is the data structure. So in the node, we have next pointer, and we store the value. And in the queue, we have head and tail pointers, and initially the reference to the same dummy node. And to add a new element, we create a new node. We update the next pointer of the current tail, and then we update tail. And the trick is that we need to perform these modifications atomically somehow. Right? Because we modify different locations. What we want to do is to do this atomically. And let's try to build this solution. So if it's a sequential implementation, then you would create a new node, read the current tail, modify the next point of the current tail, and modify the tail pointer, right? Now we want to make it concurrent. And as typically for concurrent algorithms, we need to have an infinite loop around the whole operation. And we use combined set to synchronize between threads. And we will synchronize on adding the node to the linked list. So once the node is in the linked list, it's already in the queue. Only then we'll move the tail pointer forward. And here is the pseudocode. So now we read the current tail pointer, and we try to install our new node next to this tail. So if the next pointer is still null, then this combined set succeeds. If not, then we simply restart. But once it's installed, we modify the tail pointer, we move it forward, and finish. And let's try to see how it works and whether there is a problem here. So we have two threads that will perform enqueue. And the first thread, the yellow one, creates a new node. It reads the current tail and installs this node right after the current tail, and it gets preempted now. And if now the purple thread comes, then it observes that the next reference of the current tail is not null, so it can't proceed. So we didn't use locks here, but we designed a blocking algorithm. How to fix that?
Why is it blocking? Someone is going to make progress, right?
But here, if the yellow thread gets preempted after installing the new node to the next field and before updating the tail pointer, then we get into this state. And when another thread comes, like here, the purple one, it comes, reads the tail pointer, tries to install its own node in the next field, but it's already not null. It can't do that. So it tries again and again.
Yeah, but the yellow thread, when it's walking up, it finishes.
Yeah, sure, but then any algorithm with the locks would be non-blocking, right? Because if you acquire the lock,
No, it's just a technicality about the definition. Definition of non-blocking means that someone makes progress. What you're saying is it's not wait-free.
no, what I'm saying that it's not lock-free actually, because for it to be lock-free, we need to guarantee that independently on what other threads do, one of them, at least one of them, makes progress. And now if one of the threads gets preempted, then others can't make progress.
I disagree with your definition of block freedom, but okay. I think if yellow thread will come back at we will finish. Right?
Yes, if the yellow thread comes back,
But it will come back, right?
it will come back. But until it comes back, we kind of locked the state of the queue.
This is not the right definition. A blocked thread is a thread that's not doing anything. The scheduler is moving away. But
Yeah.
In this case, we spin in a while loop. It's not a block. It's a
Which one? We can if the yellow thread gets preempted, right? Then other threads, they can't finish.
because the condition will fail and will spin
Yeah,
again and again, right?
yeah, exactly.
It's not a blocked thread. It's a thread that is
But how do you define blocked? If it can't finish infinite number of steps, then it's blocked.
it's hanging. It's a live block. It's not a block.
It's non-blocking. It's not wait-free, but
It's not free, it's not lock free, it's not even abstraction free.
it's lock-free.
It's no, it's not lock free.
It is definitely abstraction-free.
No, it's not.
Why not?
Because it's not non-blocking. You see, because if one thread gets preempted, then others are stuck.
Okay, but let's take it offline.
So it's actually fine, you can check the definition, but
We checked.
check it again. But what lock freedom guarantees is that it guarantees system-wide progress. What wait freedom guarantees is that any operation finishes in a bounded number of steps. Okay? Yeah, sure. What you can do is that you can, if you can't install the node, so you observe situation when the tail pointer, the next field is already updated, but the tail pointer has not been updated yet. You can help with that. You can update this tail pointer. You can do this via compare and set. right? So you do this on the normal path. You move the tail pointer forward, and this cast may fail because other threads can come and do the same here. So if they try to add the node with their element to the linked list, and this combined set fails, then they move the tail pointer forward and restart. And this way we make sure that we are not stuck. So we continuously move forward and forward. Okay, so that's how NQ works. And in our example, in this situation, when the yellow thread got preempted after installing the node, but before updating the tail pointer, then the purple one helps with updating the tail pointer. So now the data structure status is fixed. And then if now the yellow thread awakes and also tries to update the tail pointer, then it just does nothing because it has already been updated by the purple thread and finishes. And the yellow thread starts from the beginning and will successfully add the element. Well, that's how Anki works in the classic Michael's code queue. So, maybe questions here? No questions. And the deck is much simpler. For deck, we simply move the head pointer forward. And after we moved the head point forward, the node that was the second one becomes the first one and becomes the new dummy node. So after this action, we have 2 and 3 in the queue, and 1 has been extracted. So here's an example. So we read the current head, we read the next pointer, and it's possible, of course, that the queue is empty. So if there is only 1 node in the list, the queue is empty. So in this case, we return null, but in our example, it's not empty. And then we try to move the pointer forward by comparing set to synchronize with other deck queues. And on success, we read the value of this next node, which contained the first element, and finish. Otherwise, if another thread has modified the head pointer, we try again. So that's how enqueue and dequeue work in Michael's code queue. And in our example, we'll slightly modify it. We will simplify the Michael's code queue, and we'll make it single consumer. So it's a standard pattern in concurrent algorithms. When you have only 1 thread that can do something, like for queues, there are a lot of single consumer or single producer queues, or you can find a lot of single write data structures that allow multiple readers. So in our case, we have single producer queue, so we don't need to synchronize with the other deckers. Oh, sorry, it's Paul here now. So we don't need to synchronize with other instructions. Here can be only 1 thread that extracts the first element. So we don't need these infinite loops, campaign sets, because no one to synchronize with. And in the repo, I have this Lincheck test for the Michael's code queue. So we specify the initial state of the Michael's code queue, the operations on it, and we run a test. And let's see what happens. So you can run it. So let's run this test. Let's run it. And if you run it, it should fail. Right? It fails with this error. Why does it fail? Exactly. So this test doesn't know that our queue is single consumer, and in this scenario we see that we call poll from different threads concurrently. So we need a way in Lincheck to explain such contacts. And that's how we do that. In Check, you can say that some operations can't be called concurrently, and you can even group these operations. Like you have poll, or maybe you also have peak operation that only checks, only reads the first element. And all these operations are consuming operations, so you can say that all of them can't be executed in parallel, and all of them are in the same group. So here we have only one operation, but it could have been several operations. And now, if we add this parameter to the poll operation, Lincheck does know that the poll should be called only from one thread. And if we now run the test, it doesn't fail. So let's try to do that. Let's spend a couple of minutes on that, and then we'll fix the test together. So the question that to understand whether the results are correct or not, Lincheck tries to find a history, sequential history that explains these results. And if there is no one, then potentially we need to generate a lot of such histories, right? And to check all of them. But of course, Lincheck doesn't generate all of them. It checks them not so naively. It tries to iteratively build such an execution. So, for example, so for example, you have two adds from different threads, and both of them succeed. So you try to build a sequential execution. You start with, okay, you have two adds and one of them fails. You try to build sequential execution. You start with the add that has failed, but when you begin with it, it succeeds, right? And in this case, we simply don't study this part of the tree. So we say, okay, we don't need executions with this prefix because they already do not match our results. So we don't check all the histories. But yeah, in the worst case, we can check many of them, but in practice, it's fine. It's not like we spend a lot of time in the verification phase now.
So is there still a possibility to pass
Can Lincheck guarantee something? No, because it's a testing tool. It generates random scenarios, and probably your bug can be discovered only on a specific one that wasn't generated. And the model check under the hood is bounded. So it's bounded by the number of context switches. And it's possible that you need more context switches to discover your bug. So that's why, for example, in practice, we run Lincheck tests for maybe 5 seconds regularly, but on the nightly builds, we run them for 10 minutes or so. Because in this case, Lincheck has more time to study more scenarios and study them deeper. But it can't guarantee you anything. It's not a formal proof. It doesn't prove that your implementation works, but constructing a formal proof is a very complex task. And constructing a formal proof of a practical algorithm requires not only spending months on building such proof, but also spending time on maintaining this proof when you change the algorithm. But with the tests, it's simpler. You spend, 2 minutes to write a test, and then you are almost sure that your data structure is correct. And with the formal proofs, you usually prove the core algorithm, but not the implementation. You can prove the implementation. And that's what people sometimes do, but it requires even more effort. And then I would say that in practice, it means that this particular algorithm is so important that you can invest really a lot of resources to prove it formally, but in most cases you don't want to. You have neither resources nor expertise. All right, so let's do that together. So we have this. Where is this? This microscope Q test, and if you run it, then we see that it fails. It should fail. No? Yeah, it fails with exactly this scenario. When we call poll from multiple threads and both of them extracted 0, but it was added only once. So now if we say that poll can't be executed concurrently, so we add this in parallel group, say that, okay, it's consumer. Then now if you run the test, then the check never puts poll different threads, and this test succeeds. We can wait, but trust me, it will succeed. No or yes? Yeah. It should. It should. Let's wait.
So while waiting, it's just generating more.
Yeah, yeah. Half a minute with default parameters. Yeah. Yeah, we're using check for production. I will talk about this. Okay.
And how do you integrate it into your continuous integration pipeline, and how might
Okay, I can answer. I will talk later about using check at place in Kotlin, and regarding continuous integration, it's just a unit test. You see, so here's just a unit test. We have we run it with the JUnit, and
it runs for this well.
okay, you can the short. The short answer to that, you can tune in check so it can the execution time is smaller, and you run fast tests with kind of fast mode by default, but you also have a naturally built or maybe a separate build to study your data structure deeper and more thoroughly. All right. So let's go back. Abstraction freedom. So what abstraction freedom guarantees us is that you have multiple threads, you have concurrent operations, and if in any state you stop all the operations, you stop all the threads, then you can continue any of them and while other threads are paused. And this thread will finish the execution in bounded number of steps. So you stop all threads but one, and this one can finish in finite number of steps. That's what abstraction freedom is. And actually, the model checking mode in Lincheck, when it studies interlinks, that's actually what it does. When it studies new interlinks, it tries to run. It switches at some point, and then if it doesn't know anything about this switch, it finishes the thread to collect a set of shared memory accesses where it can switch later. And when studying this thread, it can observe that your operation hangs or your operation blocks because of acquiring a lock that is already acquired by another thread or something like that. And if you observe that you can't finish, then you detect abstraction freedom violation. And then in check, you can check that your algorithm is not blocking, so abstraction freedom is the weakest not blocking progress guarantee. You can check it by modifying your test this way, by adding check abstraction freedom in the model checking options. So let's do that in our test, and let's see what happens. So if we do that, let's try to do that. So we add just this one line, we run the test, and it fails. It fails while we were adding 2 elements concurrently. So let's take a look at the slides, it's more convenient. So we add 2 elements concurrently, and here we first create a new node, we read the current tail and add this node to the next to the current tail. Then we switch, create a new node, and then we can't proceed. Why? Yeah, that's because we don't do helping in the implementation I gave you. If you take a look at this implementation, if this component said that installs the element to the next field, install the node to the next field. If it fails, we do nothing. We simply retry and we retry and retry. So here's a spin waiting loop, and it's not abstraction free. Some disagree, I know. What?
I agree with you.
Oh, you agree with me. Thank you. So and then check detects that your algorithm is actually blocking. So if we fix the algorithm, then the test will pass. Let's fix it. Let's add helping to this algorithm. So, how should we fix it? Can anyone help me? What to do? What should we do? How to fix this add? Add else block. Okay, where? Oh, okay, there's only one if. We have else block. Should it work now? No. So in this else block, we need to help with moving the tail forward. For that, we can simply, we expect that it's still current tail, and with the next point, we know that it's not null, because otherwise the compare set would have succeeded. So we do know that it's no longer null, so we can safely read it here. And now we added helping to our add function, and we rerun the test. Let's rerun the test, and it will succeed. Well, at least I hope so. Yeah, so it works fine. So that's how you can check whether your algorithm is not working or not. You can't check whether it's log-free or weight-free. Unfortunately, it's not so trivial, but for abstraction freedom, you can add some checks to the test. And the last thing I want to cover in Lincheck is that you can also validate that after the execution, your data structure state is correct. So for example, in our queue, what we can check is, for example, that the tail, the tail pointer references the last node in the linked list, so the next field is null. And we also can check that in the dummy node referenced by head, we don't store any element, because if we do, we have a memory leak. Once we extracted the element, it should no longer be in the queue. And it can be fine for languages without garbage collection, but for JVM, for example, yeah, that's what you really want, because if it's still in the queue, then the garbage collector can't collect this extracted element once it's no longer needed. So that's what we can check. And let's add these checks together. We go to the test, and to add this check, we simply add a new function that we validated. Let's call it validate. And we annotate it with the validate annotation in Lincheck. And here we invoke like queue validate state. Right. So we create such a function. Usually you don't want it to be public, you want it to be internal. And what we can check is that, okay, that the element in the head is null. Okay, and we want to check that tail is the last node in the linked list. So we read the tail pointer, we read the next pointer, and check that it's the last one. Tail next should be null, right? So we validate this state validation. And now we can, after each of the scenario running, Lincheck will call this validate state function that will fail if one of these invariants are not satisfied. So if we call this test, we observe that, oh, our data structure has failed. Let's go to the slides, and we see that we added one, then we called poll, and then the validate state function has failed with the error that head value is not null. And the state was that the dummy node still contained the extracted element because we didn't clean it. And if we fix the code now, so we go to our poll operation, and here we not only return the element, but we also clean the field. So let's clean it. Now, once we clean the extracted element, then our test should pass. We actually use this feature pretty often, especially when dealing with concurrent linked lists where you can remove elements from the middle. You want to be sure that your logically removed nodes are also physically removed, and you want to make sure that no logically removed or processed nodes are reachable from the data structure. And that you can do with this validation function. So any questions here?
When talking about the simple data structure, it's supposed obvious to try adding any integer numbers. But if you are testing a little bit more complex structure, are there a way for us to assist on constructing it?
But it still works. If you have a complex data structure, Lincheck successfully finds errors, and you will see that.
Okay, what I'm worrying about is that we'll try to guess the number, right?
We try to guess what?
Try to generate the input relatively randomly.
Yeah, we generate it randomly. Sometimes it's not, it doesn't work perfectly, but you can improve that. There are techniques, pretty known techniques. We just didn't have resources to implement them in Lincheck, but even generating scenarios randomly works pretty well. So I would say that in practice, when I develop a data structure that's going to be used in production, then I don't trust myself. I don't trust my colleagues in verifying this data structure, because sometimes it's just hard to analyze complex code. You don't see all the corner cases, but if you run in check test and you run it for an hour and it passes, then you're almost sure that everything works correctly. But it's not proof here. And it works pretty good on a big scale, so I will discuss it, okay? So in a couple of minutes. Okay, so, and with Lincheck, actually, we developed it because we write concurrent algorithms in Kotlin, specifically in Kotlin coroutines. We have a lot of concurrent primitives under the hood, and we need to test them. And when we added Lincheck to test these algorithms, we found a ton of bugs. Here are some of them, and all of them are fixed now, so no worries. And what is more important is that we didn't introduce a lot of more bugs, because we catched them at the testing stage. And we also tested popular libraries. And for example, we tested GC2's library. We found non-linearizability issues there. Yeah, here's Alexander who found the bug. And we also managed to find a bug in the standard Java library. Here's a concurrent linked deck data structure that doesn't work, and there were multiple attempts to fix it, but unfortunately it's still non-linearizable. And what's happening? Because, oh wow, some lag. And let's write a Lincheck test and reproduce this bug in concurrent linked deck. And unlike these small data structures we've been working with, right now, concurrent linked deck is a pretty big one. And the In concurrent we have even more complex data structures. We developed new channels, and the implementation is, I think, 30,000 lines of code, more or less. So it's pretty big algorithm, and we're happy with using the check, so no issues so far. I mean, we did find a lot of bugs, so it's not like no issues. We didn't find any bug. Everything works perfectly. No, we found and fixed a lot of bugs while developing the algorithm, and now we show that it works correctly. So let's try to rediscover this bug. You can write a simple Lincheck test, specify these operations, run the test, and you will see why the concurrent link tag data structure from the standard library doesn't work. Let's try it together.
I mean, do you have this check abstraction?
You don't need it. Yeah, no. There is a linearizability error actually. So how to create a new file? Oh, sorry. Concurrent link deque Lincheck test. Fun test. Oh no, it created it. Not in the test directory. Yeah, let's move it. Model checking options, check. Okay, so we have that. Now we can run the test. Now we need to specify the initial state. Current link. Concurrent deque is deque, sorry. It's deque. Let's store integers here. And now we have several functions. Fun. Add first, which takes item and delegates this to this first here. We can copy and paste this. Call add last. At last. And the same with all other operations. Pick first, for example. So it doesn't take arguments. So it's pick first, pick last, I guess. Pick last, pick last. Also poll first and poll last. And the last one is poll last. Okay, so here are all the operations, right? Let's try to run this test. I hope it will fail because I didn't check on my laptop. It should fail. Yeah, so it fails. And it takes time to understand the error, of course. But here what happened to that, so we have at last in the first thread, and poll first in this thread extracts this element. We also have at first 0 in the second one. And here, this information, it means that this at first was called after at the last in the first thread is finished. So it means that one operation from the first thread and 0 operations from the second one we already completed at the beginning of at first. And now this means that we call at last first. And then we then it's complicated. Let me think, because my scenario was different. So we call it last first. So we have a deck with one element. Then we call add first and poll first concurrently. And since poll first returned 1, then poll first if you try to construct sequential history, then poll first should be called before at first in the second thread. Because otherwise, it should return 0. So then it means that we called at last, then we call at last, we call poll first, then we call at first and pick last. It doesn't work. Why? Do you see why? Sorry? Yeah, exactly. Yeah, sure. It's not pick first. Yeah, I was confused. Yeah, exactly, because here pick last should return 0, right? Because here we have at last, then poll first, and after that, the element is extracted. So 1 is not in the deck, and then when we add 0 and call pick last, there is only 1 element in the deck. It's 0, and we should return 0, but we return 1. And then we have a trace that explains the error, but we won't analyze it now. What I did is I collected a similar trace. Actually, I think it's pretty much the same. And I added some explanation to the slides. And the slides will be shared, so you will be able to study this error. So here will be some slides. So you will see how the data structure changes. And trust me, you will be able to understand it. So, and the last thing I want to note that there was a reason why we had to build Lincheck. It was not only about testing, but when we were working on new channels, it was impossible to build an algorithm without proper tooling, because you develop a new algorithm, and the semantics of which is pretty complex, and you need some tool that helps you with the debugging errors. That's why we added a model checker into Lincheck. That's why we started using Lincheck. And yeah, this algorithm was merged, and regarding the question whether Lincheck can deal with the complex data structures or not, here's just a diagram of part of the algorithm. You don't need to understand it, but it's just to show that the algorithm is quite complicated. And there are a lot of corner cases. And with Lincheck, we properly tested this solution, yeah, and it works fine. So, if you work with the concurrent algorithms on JVM, I think you should try Lincheck. That's it. And yeah, you can also read our paper that was published this year at CAF. So it explains how Lincheck works. Also actually explains this error in the concurrent link tag. That's it.